Hey everyone, welcome to Devs on the Graph. We've got Ben Busch here from Hopr, who is a data scientist. And what we're going to go through in this beginning part of this Devs on the Graph episode is just get to know Ben, see why he is in crypto, what he has been doing in crypto, and then from there, we're going to go into what he's been building with Hopr. So everyone listening, ladies and gentlemen, introducing Ben Busch from Hopr. How you doing, Ben?
Hi, very glad to be here. I'm doing fine, enjoying the last sunny days in Milan, and yeah, I'm doing good.
Awesome. So tell me about yourself, Ben. How did you get started into data science? Going back maybe even before crypto, or did you start in the tech world in crypto? Tell me how you got started.
Okay, that's actually a long story. I mean, it's a long and short story. So it is that, I mean, I have never been, so I'm not a classical data scientist, neither did I had exposure to the crypto world before I started at Hopr. I was a classical researcher at the university. I did my undergraduate in economics, I did my master's in economics, and then I did my PhD in economics, which I finished in 2021. And pretty much in this time, I didn't have much crypto exposure. The first time I heard about Bitcoin was actually at the start of my undergraduate, where I had like a LaTeX coding course back in 2012. And somebody said to me, hey, there's this thing called Bitcoin and you can mine it. That's really the first time I heard about it, but I didn't pay much attention to it. And then, I mean, especially during my PhD, I was doing a lot of theoretical research. So I was always interested in basically what is the model behind like data, right? For example, when I had my economics courses in university, and it was about econometrics, right? Estimating causal effects on a data set. I was always more interested about how do we write that model behind the estimation to basically get a better understanding about what should be the right model that we need to estimate on the data. And that also, during my PhD, I was doing a lot of theoretical research on human behavior by trying to basically capture certain traits of humans in a mathematical equation. So my whole study has always been starting from a model and then going to the data. And that's how I basically then also got into coding by, hey, I have this model, I formulated it, I wrote it down, now I want to implement it. And that's where I got my first exposure basically to data and coding. And then also I got, then how I got into the crypto world is I started a postdoc here in Milan, where in the end of 2021, and then I found myself in a state where I was just rewriting my research papers. Like suddenly it was not so exciting anymore, developing new ideas and pushing them forward. Now it was about getting these papers published. And I found myself into a state constantly rewriting the papers. And then I thought, like, look, I want to do something else. I think like I have transferable skills to data science. And I thought like, hey, I have done research on networks, theoretical research. Hey, the blockchain is a big network in essence. And basically I started saying like, hey, but if I want to apply for some jobs in the crypto sector, I need to have some project. And I basically downloaded this data set of CryptoKitty NFT transactions. And that's basically, I visualized the network, I analyzed the statistical properties of the network. Basically, how are holders with large CryptoKitty collections correlated to holders of small CryptoKitty collections, and so on and so on. And basically, this is basically how I got going, and I really like it. And that's how I applied then to Hopr, which has nothing to do with CryptoKitties or anything like this. But I thought like, hey, I could imagine working in this industry because I have transferable skills to data science due to my economic education, and I have transferable skills to, let's say, the blockchain itself because I've done theoretical research on network. I'm good at game theory, I'm good at graph theory, so why not try it? And that's basically how I ended up.
It seems like you have a good fit with crypto and your economics and also your interpersonal analyses, your well-educated PhD. And then now you're saying, oh, CryptoKitties, like that interests you. It's funny how that happens. I got introduced to crypto with CryptoPunks. When I first started going into really trying to understand what is crypto? I said, well, CryptoPunks, that was big. And so I said, all right, let's dive in. And I actually found the graph subgraph, and I was looking at CryptoPunks and saying, oh, this is something interesting for me, and just gathering that data. And as a data scientist, you naturally look for this data. You naturally just hop in. And now that you're at Hopr, how are you using data? How are you using your data science background to help out the Hopr team in your day-to-day? What are you building with Hopr?
I mean, basically, Hopr, we are like transport layer level privacy. That's what we're building at Hopr. So basically, we're building a decentralized mixnet. So it is a network. And within Hopr, I basically do a lot of data science around this network. Let's say, for example, currently, since we want to scale this network on a controlled basis, right? We need to basically register nodes in the network. And who comes into this network and who comes in first basically gets decided by who has how much stake do people have, how much NFTs do people have. We have this registry NFT. And basically, I use data science basically to create, for example, these onboarding lists to onboard people to the network. I do things like all transactions that Hopr does is done in crypto. I gather all these transactions, for example. I put it into a format that external accountants can use it and use it for their financial statements. I use data science at Hopr to get certain statistics about the network, like how healthy it is, how the rate at which it grows. I analyze the latency in the network, how private is it. And then the thing I'm going to talk about today, also in the workshop, me and my team built this app where I basically created an economic model for how we distribute certain kind of data in the network, and then also implemented it into the app itself using then diving a little bit into data engineering.
Very cool. Well, before we get into that workshop, and for those listening in, there is going to be a workshop at the end, so stay to the end where Ben will take us through what he's building with Hopr. I want to talk about a little bit more of the heart and soul of really what pushed you away from the academia. You were doing papers and rewriting, and you said, I got to do something different. And I want to dive in a little bit more into that decision of you said, was there a moment that you said, Ben, I need to be able to find something more, and crypto seems to be it. Could you tell me more about that decision?
Yeah, I mean, it was a little bit that I felt a little bit when I was rewriting the papers. I felt like for some papers I was working on for 5 years, I felt like, look, what is really the purpose, right, of this paper? What do people get from it when this is actually published? What knowledge does it provide to the world that really will help people to make the world, let's say, a little bit better, right? That's what I wanted to do with my research, and that always drove me, right? But during my postdoc, I realized I don't feel this passion anymore for. I don't believe myself that maybe the impact that I want to make in the world is not as big as I think it is. And that got me a little bit demotivated. I thought, like, where can I make an impact, right? And I thought, like, wow, at that time when I started to think about crypto, 2021, it was like the height of the bull market, I think, at that time, right? And I was really, really interested. And I saw this project Hopr, and I thought, like, wow, they have a really good technology which can really make an impact on the world. And I can use my skills for that. And that got me really motivated. So I think the driving force for me is that I really saw in the crypto world something new that really tries to make like where it's really, I have the chance to make a big contribution to make the world a little bit better. That's really where I felt like, hey, I need to do something different with my skills and with my life in the end.
Yeah, and I I relate to that so much. I've had a few interviews with devs on the graph and lots of conversations with people in this space. And it's a consistent theme where we really, in the crypto sphere, in the crypto world, see this technology as something that is different, that is rebellious, that does have more potential for more things than the current stack of Web 2 extraction. And so we've just met, Ben, you and I, on this call, and already I relate to you. I went through a big change to go into this space, and over again, I keep on talking with people that are really willing to make that change and do something that does push against the grain. So I'm really happy to have you on here and to share your story with other people. So knowing what you know with your education, and then knowing that you have that heart and that push and that drive to better the world, let's connect that. I want to really understand specifically how you think Hopr is helping the world and how you think Hopr is really making change for good in the world. Could you kind of dive into that specifically about the value proposition that Hopr has and why you're motivated to help Hopr succeed?
Yeah, for sure. So the thing is what I said, like we build like transport level privacy. And what that means is you need to imagine Hopr in its core as like a more private version, a Web3 version of your classical VPN, right? Just more private. And we think that this is really something important and missing to have full stack privacy in the Web3 world, because basically what it prevents is that external services like harvest your IP address and use it to basically, because your IP address is your most single unique identifier, try to harvest it and try to de-anonymize you or use it to censor you or the services you like to interact with. And here I think by building this mixnet at Hopr and basically being able to obfuscate these metadata, so the data about your data, like your IP address, we are making a real contribution or a real contribution to the Web3 by giving people a choice to regain, not just have self-custody of their money that the blockchain provides, but also get self-custody of the data, right? Have a choice which data they want to expose to certain services. So on the one hand, the thing that makes the blockchain so powerful, that it's transparent, that everything can be observed on chain, is at the same time something that is also has the potential to expose your privacy or even more than in the Web 2 world. And that's why we're trying to build at Hopr something to basically give you the choice to also have to use the powerful technology, but in a private way.
Yeah, absolutely. I relate to that so much. Before I got to work with Edge and Node, I was working with a team that was working on soulbound tokens. And I'm not sure if you understand the primitive of the soulbound token. It still is in its very primitive of its primitive stage, but very much important to have privacy, identity, reputation managed in a very healthy way. And so, yes, I love the transparency and permissionless nature of the blockchain, but I see the value very much in having a certain level of gating with this information. It's very important to make sure that if Web3 is going to be a fantastic success, there needs to be different levels of this data's privacy and making sure that there's certain levels of security. What is a certain use case that connects to you about Hopr and blockchain? Is there a certain use case that you say, man, this would be fantastic in its use and a real home run for Hopr and blockchain technology?
Yeah. One thing is if we think about wallets, right? How does a wallet work, right? So for example, when you want to send a transaction from your wallet to, let's say, another wallet, then for example, your wallet makes, like, for example, a get balance call, because to execute this transaction, it needs to know what balance you have, right? And what does it do? It usually goes to an RPC provider, like the background providers that make all the machinery of Web3 run, which is really nice. But basically they are closed source black boxes where we don't know what they are really doing, and we need to trust them in essence. And what we basically Hopr provides you is, in this wallet use case, you can do still your transaction, but all your RPC calls, they get routed through the Hopr network, basically obscuring your IP address in the process, for example. And therefore you can, like with the classical VPN, execute these transactions still, but nobody knows your IP address. in the process.
Awesome. That's wonderful. So this is Devs on the Graph. And so I do want to ask, when you're interacting with blockchain data, how are you using a subgraph? Is anyone diving in? I know Hopr has a subgraph that they're using. How are you and your team using a subgraph?
Yeah, so we have a subgraph, and it will actually also, it's part of the workshop, so stay tuned for the workshop later. But for example, how I use the subgraph in my specific case for the application that me and my team built is that we want to inject traffic into the network to basically provide some noise in the network so that the real traffic that goes through the network has an additional layer of protection by, let's say, imagine that like, hey, to identify a leaf on an open street is very easy. But if you build a forest around that leaf, then it's very difficult to identify, right? And basically, but not just to provide this privacy, also what we have is an incentivized mixnet. So basically, we should be able to pay people to relay these data, which I also will get into later in the workshop, so stay tuned. But what it means is I need to know how much a node in the network has available in stake. And this is where subgraph comes in, where I basically link information about the node that is in the network to their stake that they have in their wallet, and therefore be able to compute how much traffic I should inject in the network given the distribution of stake that is present in the network. So for my application, which I will show later, subgraph is an integral part of this application.
That's awesome. Yeah. And just as a small anecdote, one of the very first days I was working with Edge and Node, I was able to meet Sebastian, who you work with, and that was at ETH Denver. And that was in that exact moment, the subgraph went published to the decentralized network on the graph. So I was there in that moment, and so that subgraph is decentralized on the graph network. And so that was a very cool moment that I got to share with Sebastian, and also just seeing your subgraph operational on the graph network is a really, really cool thing, where you were saying RPC information is in a black box. Well, right now with your subgraph, with Hopr subgraph on the decentralized network, that's a really very cool thing that is not a black box and is able to be seen and actually permissionlessly accessible by the world. And that data set is now here for use if anyone else wants to query it.
Yes.
So that's really cool. So.
And exactly, we use the subgraph in the essence to provide privacy in a correct way and to incentivize nodes to provide privacy for others in the network, right? So therefore, it's really important for us, this subgraph.
Awesome, awesome. Well, Benedict, it has been awesome to get to know you, to get to know what you're building. I know that you've prepared a workshop that you're going to be recording and putting on the end of this interview. For those that are listening out there, Ben, could you give a short preview of what you're going to be showing for this workshop, and then we could end the interview right there?
Yeah, sure. So the workshop will be about basically a short introduction into Hopr, and then basically the application that is the covered traffic app that me and my team built that uses the subgraph that I just talked about to basically inject random noise into the network to provide an additional layer of privacy for the users of the network. And in the end of this workshop, I will also show how we basically query the subgraph and use that information specifically that we then use to, like I said, compute the amount of traffic we need to inject into the network.
Awesome. Awesome. Well, Ben, thank you so much for joining me on Devs on the Graph. For those out there who want to check out Hopr, I'll put links in the description down there, as well as any more information about this workshop that Ben would like to share. Thank you so much for your time, Ben. Thank you for joining me on Devs on the Graph, and enjoy the rest of your day.
Thanks for having me. Hi, welcome to the workshop. In this workshop, I will talk a little bit more in general about Hopr, what we are doing and building here, and also specifically talk about the application that me and my team have been building to inject data into the Hopr network to provide privacy via noise and incentives. And to achieve this, we are using subgraphs. So in the end of the workshop, I will dive a little bit more into the subgraph that we're using in the application to achieve the goal of privacy and incentives. But as a disclaimer, at Hopr, we work on transport level privacy, and that's pretty important to understand. So you can think of Hopr as a Web3 version of your VPN to transmit data privately. Let me dive into it. So this is what we call at Hopr our naive little wonderland. And imagine yourself as a user here depicted on the left-hand side of Web3. And on a daily basis, we interact with decentralized infrastructure that ensures freedom of choice, fairness, and the inclusion of everyone. I mean, that's why we love to use it. However, without proper transport level privacy, exposed metadata like your IP address, which is the most single important identifier of your identity, can be used to disrupt, exploit, and censor users and the services that we use. And at Hopr, we are a decentralized, incentivized mixnet that obscures all metadata, including the IP address, making it impossible to tell anything about who's communicating and what data they are sending. Therefore, we give people the choice to retain full self-custody of their data. And like I said, Hopr is a decentralized and incentivized mixnet. And basically it ensures complete data and metadata privacy for everyone who uses it. As you can see here in the picture where the data enters at Alejandro and goes out at Zoe, data is relayed via multiple hops, so no one but the sender and receiver know the origin, destination, or content of the data that has been transferred. So the first privacy feature of the Hopr network is this multi-hop relaying of data. Then if we look further, another privacy feature of the Hopr network is packet mixing, which makes it even more private compared to VPNs or Tor. That means data is not just relayed through multiple hops. At each hop, actually data that comes in the network is actually also mixed. So that imagine this, it comes to one relay node, it's getting mixed up, sent in different directions, and then it's assembled at the end again, providing additional privacy. And another thing that makes the Hopr network actually unique, because let's be honest, there are mixnets out there, but the thing that really differentiates the Hopr network from other mixnets is what we developed at Hopr, which is called proof of relay. And basically, it's a trustless way to reward node runners for relaying data packets. That means node runners are paid via the Hopr protocol itself using the Hopr token. And what does it mean is that we don't require nodes in the network to, because let's say they believe in privacy, they want to cooperate, to basically run a node and relay data for free. No, we basically incentivize them in a trustless way so that we believe that this is the key feature that the network will eventually scale, because people do not need to run a node because they want to do it voluntarily. No, they get paid for it and make a profit, and therefore have an incentive to run a node. And what this proof of relay mechanism does is basically that first, you don't need to trust the Hopr association. So we don't need to store any data about individuals in the network so that we are able to pay them for the services. No, the reward is directly encrypted into the data package that is sent. And as you see here in this little picture, so you don't need to trust the Hopr association, but you also don't need to trust any other node in the network, because let's say here in this example, if we start here now at Alejandro, who sends the data to Betty, to Ciao, to Dimitro, and like Betty or Ciao or Dimitro, they can only get their reward as depicted in this illustration if actually the next downstream node can confirm that they did their job of relaying data. And that really distinguishes the Hopr network, and eventually will lead to making it scale from other mixed nets that are out there. Now let me talk about covered traffic. So me and my team built what we call the covered traffic ad at Hopr. And what this app does is it issues data in the form of messages that get relayed in the network, and therefore adds noise, as these messages are not real data, therefore privacy, as there's always enough traffic in the network. And since I talked to you earlier about that Hopr is incentivized in mixed net, therefore this provides incentives, as each relayed messages that we issue through the app provides like a reward for a node runner that actually relays this message. But I will get more into it now. But let me first introduce, like on an illustration, which I depict here, the basic principle of what is covered traffic. And now let's abstract away for a network for a second and just focus on the idea of covered traffic. I made this little illustration where there's an adversary standing outside the door, so it cannot look into the room, but knows that there are two people in the room because the adversary saw them going into the room. But the door is closed, he cannot see them. And these two users are talking to each other. And the adversary's goal is to basically find out who's communicating with whom. And the adversary knows that there are two people in the room. So in this case, even though the adversary doesn't see who's what they are communicating about and who's communicating with each other, he still knows who's communicating with whom, because there are only two people in the room. So in a network sense, is if there are just two people communicating in the network, in other ways, it says only one data packet sent into the network and comes out of the other network. Somebody observing the network from the outside immediately knows what is the what these people are talking about, or which data package get relayed, right? So all the privacy feature that I mentioned earlier, like one hop, packet mixing, they don't have byte anymore because there's just too less traffic in the network. So how do we solve it with covered traffic? And here, what it basically does first, let's stay with the illustration. How about putting more people in the room? Like, even if the adversary sees all the people going into the room, now suddenly he doesn't know anymore, once the door is closed, who is actually communicating with each other. Or in other words, the task of identifying who's communicating with each other becomes now much more difficult. And now the other privacy features that we have, one-hop packet mixing, they suddenly get a lot of byte and provide huge privacy to the network. And like I said, in a network sense, it means it's like, hey, if we have enough traffic in this network at all times, then it becomes incredibly hard to de-anonymize individuals in the network or message communication. So in essence, if I need, as a conclusion, what we build here at Hopr is that CT blends random messages, noise, into the Hopr mixnet to obfuscate the real communication traffic. So there's real traffic going on in the network, maybe by just two people communicating with each other. However, with the random messages that the CT app injects into the network, we cover up these messages, like in the illustration before. And this is how Hopr protects real communication traffic from global passive adversaries observing the network and compromising privacy. For example, intersection attack. And what I mentioned before in the illustration is like also a simple illustration of an intersection attack. If there's just two people communicating and you see what comes in on one side of the network and there's only one thing that comes out of the other side of the network, then it's very easy to correlate. In this case, you can perfectly correlate what comes in and what comes out and intersect these messages and figure out who's communicating with each other. Now let's talk about the cover traffic app in specific. So now that you have a very good understanding of what cover traffic is, let's talk about how me and my team implemented it as part of in Hopr. And what I want to pay attention to is this is a basic structural overview of the app. And I will try now on a high level, basically go through it. And also this will show how we integrate subgraphs into it and show how a subgraph is crucial for the underlying distribution of cover traffic. And I want to put your attention to the bottom left here first. So we, as the Hopr Association, for now in the first initiation of the app, control four nodes in the network. The long-term goal is for this app that each node should basically in the network have its own incentive to issue cover traffic. So we as a Hopr Association do not want to control nodes. But for the version 1, that's what we are started with. And yeah, what these 4 nodes do is we call them net watchers. And net watchers are just in the essence Python scripts that are attached to this node. So basically the Python script of netwatcher 1 tells this node what to do. And what these netwatchers do, as the name suggests here, is they basically check the network. You need to imagine that they ping nodes in a network, all other nodes in a network, and record these nodes, like say like, hey, node X is available, node Y is available. And they store the latency of this ping that they get, the pong that they get back from the ping, how long it takes to reach a node. And each netwatcher does it. And why do we have multiple netwatchers? The reason is pretty simple. First, we don't assume that each netwatcher has the same picture of the network. Therefore, having multiple netwatchers allows us first to get like a broader overview of the network. And second, if the network scales, then also we can scale the amount of netwatchers accordingly to always get the most accurate picture of which node is available in the network. This is the first step. Then what happens then is these information, as the name suggests here, get aggregated by a Python script, in essence, that we call the aggregator. And the aggregator, what it does is it just takes information it receives from all netwatchers about who's available in the network and creates a unique list of nodes in the network that are available by a list of netwatcher. Let's say node X was seen by netwatcher 1 and 2, and node Y was seen by netwatcher 1, 2, and 3. And these netwatchers are then what is possible that the aggregator, for example, orders them netwatchers by the ping latency that they received. So for example, if netwatcher 1 have a better connection to node X than netwatcher 2, then netwatcher 1 should be actually the one who maybe in the end issues the traffic to him because the latency is lower. So this all is stuff that the aggregator does. So this aggregated data set of available nodes in the network gets then saved to a metric table that can be queried via SQL, for example. And then this metric table get read by the economic handler. And the economic handler is basically where the magic happens and where subgraphs are integrated. So like I told you before, a crucial thing is that in cover traffic is that it should provide privacy by providing noise in the network. But second, it should also incentivize nodes to run their node, right? By issuing these messages, nodes relay these messages, they get, according to proof of relay, they get the reward. But what is crucial here, that nodes, in order to be able to run a node in a network, they need to stake Hopr tokens in the node. And this is, and basically a node that has more stake should also receive more reward, not just because it has more stake, because this higher stake allows this node basically to relay more data, because it has more funds available to relay more data for the network. Therefore, first it should get, because it does like more work, it should get more incentives. But on the second time, but also it needs more privacy because it relays more data, so it needs more noise to cover the real data in the first version of the CTL. And therefore, I need to know somehow how much stake a node has deposited. And here it becomes very important to understand that a node is always attached to a safe on Gnosis, a Gnosis safe. So Gnosis safe has an address. There are the main funds of a node stored. Then a node has like a node address. It's an Ethereum address that can take funds from the safe where the funds are secure and basically open a channel to any other node in the network. And this channel that this node funds can then be used to relay data messages. And now comes the big question: how do I know how much funds a node has? And therefore, we use a subgraph, because with a subgraph, we can know by basically getting all the nodes that deployed safe on Gnosis safe. And also, we can merge this information with the smart contract of the token itself to get the idea, to get like the link between how much at each single point in time is deposited in stake in a given node. And this is exactly what I will also emphasize more in the coding, in a little coding example later, where we'll go through code and how we actually merge this data and how we use the subgraph in specific. But as you see, the subgraph has like a crucial part in this cover traffic app, because it is the basis for actually doing the cover traffic calculation of how much incentives nodes should receive. And another thing that the subgraph does, is an integral part for us, is that in the first version of the Hopr network is actually permissioned. Our long-term vision, of course, at Hopr is that the network is permissionless, so that each node who wants to enter the network can enter the network. However, we want to be able to scale the network slowly to basically deliver the best product possible and to have some control over network size, so that a too large network doesn't break it essentially. And therefore, nodes need to register for the network. And then we have another smart contract, which is the network registry smart contract. So node needs to register their safe there and their node. So since only registered nodes are eligible to receive cover traffic, I need to know who's eligible. And that's a third smart contract that I merge using a subgraph to actually figure out not just how many funds does a node have available, but also how whether it is eligible or not to even participate in the network. And this subgraph, like I said, I will show in the end. And then I don't want to go into much detail, but then the economic handler does this calculation, and you can look at the code. There will be links in the description of this video where you can look into the code. But the economic handler, in essence, calculates then how much cover traffic each node in the network should receive, depending on their stake, availability, and whether they are eligible in the network or not. And what then actually happens, this calculation, the of that economic handler does is basically saying like, hey, node A should receive this amount of messages, node B should receive that amount of messages. These tasks basically go to a RabbitMQ broker. It's a message queue, and this message queue gets read by postmans. It's another Python script attached to the same node as a netwatcher, but what the postman now does, it has the availability information from the netwatcher. And based on this availability information, now can efficiently distribute these messages according to the task that the economic handler provided to the queue. And then these postmans distribute the messages that other nodes then relay. And by doing this relaying job of the data, they earn the incentives and provide privacy for the rest of the network, as they always relaying messages, so generate noise in the network. Then what messages they relay, this information gets back into the queue, back to the economic handler, who stores this in a reward table, where we can then see metrics of how many messages have been relayed, what reward users are earning, and so on. So before I jump into the example of the subgraph, let me just give you a brief overview of the current state of the Hopr network. Currently, we have more than 300 running nodes with over 90% availability. You can check that out in our network dashboard. And again, all these links will be in the description. What we do with this application that we build is we provide supply-side revenue and privacy for node runners by cover traffic. You can check out the GitHub repo of this and see the code. Everything we do is open source, so you can just check it out. More than 3.7 million Hopr are staked currently as a recording of this video, and node runners, it's very profitable. They earn like an APR between 10 and 15% for relaying these data packages. So this is privacy and at the same time incentives injected into the network by the application that we built. Of course, that's not the only thing. We also have our first product, RPCH, that has launched. And it's the first private gateway to the blockchain and provides demand-side revenue for the Hopr protocol. Here's actual wallets doing the RPC calls, like I introduced earlier, we talked about in the podcast. And this RPC call, instead of going to the RPC provider directly, is routed through the Hopr protocol. And therefore, by relaying this now real data, right, that needs to be hidden, here users earn the normal reward for relaying messages. And these real data that gets relayed through the network through RPCH, they get covered by the noise that we provide with the cover traffic app. And then all the privacy features that I mentioned earlier, one hop packet mixing, really have a bite and provide privacy for the metadata of these transactions. And RPCH, there will be also a link in the description. You can sign up for it and just check it out yourself. Now let's jump into the subgraph. Now, finally, let's start look at the subgraph. And the subgraph, it's called Hopr nodes to 4, and the 4 is just our name for the production network. We like to name our networks like according to Swiss mountains, and the 4 is one of the highest in Switzerland. And before going deeper into the subgraph and looking at some code, let's look at 3 crucial smart contracts that this subgraph actually indexes to see how actually helpful a subgraph really is in providing us with the data that we need for our application. So the first thing is that we have this smart contract that is called Node Stake Factory. And here basically nodes, if they want to participate in the network, they deploy their safe on Gnosis chain, where they can it basically indicate like, hey, I deploy my safe. Here I deposit my Hopr tokens for the network. And what you do is then you basically make a transaction, say like, hey, you deploy yourself. And then you can see this here. There's a new Hopr node safe. So here with for example, this address was registered 20 hours ago at the time of this recording. And here you say like, hey, I want to be in the network. So that's the first information that I need, right? So who wants to be in the Hopr network, right? Then the second information that I told you I need is like, since we currently permission access to the network, nodes need to be registered, right? So basically here you see the network registry smart contract, and this event registered by managers, basically a registration by us where a safe is basically attached to a node. So here we register a safe node pair for the network. So once we do that, and once you are registered by us to this registered by manager event, you are eligible and can participate in the network. So now you have a safe. Now we say, hey, you're safe and node. You can participate in the network. Now, the last bit is what I told you for our application is that I need to know how much stake there is in the safe and in the node. And here, why do I get this? So the payment token for is WX Hopr. It's a red X Hopr token, and X Hopr token is the Hopr token on Gnosis chain. And basically, this smart contract, this token contract shows all transactions of WX Hopr token. So basically, I need these three sources of information to compute what I want to achieve with the Kava traffic app. And here now you already see that there's three different smart contracts that where subgraph is an invaluable tool in actually indexing them and merging them together. And this is basically what we did at Hopr, right? We programmed this Hopr nodes through a subgraph. And here in a feature basically that I love is the playground, where I can basically now specify the query that I want to run on the Hopr query that I want to run to get the information that I need. And here, let's just look at it. Let's use the playground. Let's shut these things down that are open here, because we have indexed a lot of things with the subgraph. But let's try to create the query that I actually need for the CT app. And now you will see how easy that actually is. So first I need to look at safes, right? Because I said like, hey, you need to deploy a safe. So I need to look at safes. Then I need to look at registered nodes in network registry. And what do I want? I want to have the node with their ID, which is the Ethereum address. And I want to have the safe with the ID. And additionally, I want to have the balance of that node. And I want to have the WX Hopr balance, because that's the payment token that we use. Now I can run this query, and here it is. So I have now registered nodes. I have the node address, I have the safe address, and I have the WX Hopr balance of that safe address. And in this case, it's for this node, it's 24,000 WX Hopr tokens. Now I have this information, and now I want to just quickly show you how we integrated into the CT app, just the basic functions. And here I made like a small script that is not the actual implementation of CT app. I just want to highlight the functions, how we actually query now this subgraph, right? Because I showed you this, subgraph here is a very powerful tool that actually lets me basically already create the query that I need. And now the CT app is implemented in Python. Let me show you this in Python on a simple Jupyter notebook. I get the credentials of the subgraph, like the subgraph URL, the IP host, and the IP key. That are not subgraph information, that are node information. And basically, then I define a function to get the subgraph data. And here, basically, what you see is this is basically the query that we already specified now together, implemented here. What I did additionally is that there might, I mean, the Hopr network will scale at some point over 1,000 nodes, and currently there are 300. So what is additionally in the query is that I included pagination, meaning that I query the first 1,000 nodes because that's at each query what the subgraph gives me. But then I paginate through this to, in case the network is greater, I query more. I can query more than 1,000 entries. So I query 1,000 entries. The skip goes to 1,000, and then I query the next 1,000 entries, basically. I store it in a dictionary. If more content is available, means that there is more than 1,000 nodes in the network. I continue. That's basically what this while loop specifies. And then basically I get this data from the subgraph. I store it in a format that I need, right? I want to have the node address. I want to have the WX Hopr balance. I want to have the save address. And I want to store that in a dictionary. And this is basically the pagination that will only stop until no more data is available. And this function then returns the subgraph dictionary that I need. And we can look at it directly. I already did it, so let's look at the subgraph data that returned. Let's look at it. In this case, there are 452 registered nodes at the time of the recording in the subgraph that are eligible. And what you can see here is directly the node address as the dictionary key of a node, and then the save address already here, and the WX Hopr balance of that node. So here already I have now very easily through the subgraph, you saw how easy it is to query this very complex information from these three smart contracts. I have the information that I need. I have a node address, I have the save address, and how much balance it has. And it was, as you see, like a few lines of code to actually get that. Now, I told you that in order to basically, that's the thing I want to highlight as well. In order to actually relay data, you need to open a payment channel to like another node. Meaning you need to say like, hey, I open a channel to you and I put this amount of funds in it, because when you actually relay data through that node, for example, the CTF, we need to open a payment channel to another node, then these funds go out of our payment channel to that node in their safe. And therefore, I need to fund channels. So there's not just WX Hopr in the safe, there's also WX Hopr that goes from the safe into the channel of a particular node. And what I do here is I query the channel topology through the API of our of the Hopr protocol. And basically what it does is it gives me for each node how much money it has deposited in the channel. That's basically what I do here, but I don't want to go more in detail. Let's look just at the data, what it gives me. So here we have 332 nodes. Out of these 452 eligible nodes actually have like a payment channel open. And nodes on the protocol level communicate via PIDs. So I have like here the PID of a node, and I have the node address of the node that initiates this payment channel. And this node address is, in this case, this one, and it has the aggregated channel balance of here 460 Hopr tokens. So 460 Hopr tokens it gives available for actually relaying messages. And then I merge this data simply here, what I show here. And if you look at it, then I get the full all information that I need basically to do the computation of the economic model. I have the PID of a node, which is identifier on the protocol level, how nodes communicate. I have the node address of a node. I have the balance that is in a channel, and I have the balance that is in the, I have the safe address and the balance that is in the safe. And also I can then compute the total balance. So I know that this node has a total balance of 10,000 Hopr tokens. And now I have everything that I need for actually my computation. And what I want to illustrate is how simple subgraph makes it for you to get this information and then merge it. And this is actually the end of this tutorial. I hope I could give you like a brief insight into what Hopr does, what we're building here, why we think it's important, and also how subgraph is like an integral part in the CT app that is invaluable for the Hopr network to provide incentives and privacy. Thanks so much.